We want to welcome our UNICAM and a PhD in statistics from Johns Hopkins University. His academic journey includes positions as research associate in the Department of Oncology at the University of Cambridge, an affiliate professor at the Cambridge Institute of Computational Biology, an honorary research associate in the Computational Biology Group at Cancer Research UK, and an associate researcher in the Department of Medical Genetics at UNICAM. Since 2004, he has been a key developer in the Bioconductor project. Currently, he serves as an associate professor and head of Department of Statistics at UNICAM. Our speaker today has so many expertise, ranging from analytical methodologies, computational tools in biology, computational biology, bioinformatics, and particularly for data generated from microarray and sequencing, experiments with applications in omics. He has published so many journal articles in international journals, and I'm sure we're going to gain a lot from his talk today. So, ladies and gentlemen, can you welcome Professor Benilton?
Thank you. Thank you all for the introduction. Can you guys hear me well? Yes. Okay. So the idea today is that I'm going to talk to you a little bit about the ideas behind machine learning and artificial intelligence with a particular view for healthcare. My expectation is that you guys will not get out of here being experts on it, but I want you to have an idea of key points of things that we think that are important within this field. So I'd like to start with the definition of something called an expert system. Okay, so let's take a look at this. What's an expert system? It's a system that emulates the human behavior on decision making. That's the main idea here. So through the cartoon, what we can see here is that the expert system is a system that would appear to be a black box that has three key parts, where let's start with this one. One is the knowledge base. This is where we store all the knowledge from a particular expert or from a field. So these could be, for example, a bunch of informations on things like when you have this type of symptoms, this is the treatment that you have to take. Then we need to have an inference engine. So the inference engine is what's going to look at the information given by the user. So the user could be like a medical doctor. The user will ask questions and answer questions to the system through a user interface. And this inference engine will take those responses, compare to the knowledge base, and return advice. This is the main idea of an expert system. But why am I mentioning this when we have like all these machine learning techniques that you guys are probably familiar with? So this is actually how it all started back in the 70s, right? So let's nominate a few of those parts. So the knowledge base, as I mentioned, is what will store the knowledge about the domain that you're working with. So this is domain specific. It's likely complicated for us to look at an expert system that is very general. It has to be specific to a particular field. I'll show you an application for that. Then we have the inference engine. As I mentioned, it uses the knowledge base. It compares with inputs from the user and gives advices. It can work actually in two particular ways. One particular way is what's called forward chaining. So it is data-driven. This means that we, for example, if we are looking at patients, we are starting with data like what are the symptoms, what's the age, what's the weight, and based on these data, we go towards the end and we have answers like it is more likely that this person has, I don't know, a malaria infection type of thing. Okay? It can work backwards as well. It is hypothesis driven. So this is set up within the inference engine. So when we are talking about hypothesis driven, we are going backwards. We're starting, okay, I think this patient is suffering with malaria infection. What can you ask, what can you, system, ask me in order to be able to confirm that? And then the system starts from that hypothesis that, for example, the medical doctor believes that that's the set of symptoms is compatible with a particular disease, and then it comes backwards. So it can work both ways, but it's not that the inference system will dynamically change. It is configured to work either on the forward chaining or on the backward chaining, okay? And then we have the user interface that is exactly what we see. That's how we interact with the system. Now, there are two other bits of information that might be interesting, but they are not necessarily in every single expert system, which is an explanation facility. So that's a feature that would allow the system to explain to the user why it is taking that particular decision. So I'll give you an idea. If here, let's say we are within an endemic scenario of dengue, and then I get a patient that has very high fever for about 10 days and a lot of pain in the eyes and pain in the muscles, right? And then I give this information to the expert system. It processes whatever is it that it needs to process, and then it returns to me with something like, there is a 70% chance that your patient has dengue. And the reason I'm saying it has dengue is because the patient has no explainable fever for 10 days and muscle pain. So this is an explanation facility that it is desirable, but it's not necessarily present in every single expert system. And there is a fifth point, that is the knowledge acquisition system, which is a set of methods that would allow the expert system to be updated and learn new information. So think about the beginning of the pandemic in 2020. So people would have like flu-like symptoms at the very beginning. And that's all we knew back then. And we would say, well, you have fever and then you have flu-like symptoms. It is likely that you have COVID. But then, as time passed by, we learned that people would start tasting things a little bit funny and not being able to smell at all. So an expert system that would be ideal would be able to learn about these two new features that were not set up at the very beginning of the system. So that's the idea that we have in terms of ideal system. This is what we would have. So back to the 70s, what do we have back then, right? So there was an expert system called MISSING. And missing is named like that because that's pretty much how every single antibiotics finish in their names, like penicillin, Bactrim, and all those antibiotics, they end like missing. Okay, so this is the reasoning behind the name. And what did that do? So it was an expert system that would identify bacteria cause infections. How would that system work? So it would actually make recommendations on antibiotics, and after that it would adjust the dosage of the antibiotics using information from the patient. In this particular case, it would use the weight of the patient in order to be able to give proper recommendation on the dosage. It was developed in the 70s at Stanford, and it was actually the PhD thesis of Ted Shortleff. Okay, so this was one of the first systems that were expert on a particular field, and it was comprised of about 600 rules. These rules, they were all of the type, if this, then do that. If this, then do that. So it was like a very complex program with a lot of ifs for those of you who program in Python and R, etc. So this was actually a small nightmare for the people programming it. The questions that the system would ask the medical doctor, they were yes or no questions. And they were also simple textual questions. So things like, what are the symptoms of the patient? And then the medical doctor could describe fever, diarrhea, pain. So this is the type of questions that the system would ask. And the nice thing about that system is that it would return to the medical doctor a list of possible bacteria that were causing that particular disease. And now the nicest thing about that is that that particular list would be ranked by the probability in terms of confidence of that particular diagnosis. It would give the medical doctor the reasons for which the system believes that that particular bacteria was the one to be guilty, and it would recommend a drug treatment. So this was the very beginning back in the 70s. Of course, there were quite one or another particular interactions before that, but this is the one that actually was highlighted over the years as being one of the very first expert systems. Now, what were the challenges for that particular expert system? The top one was the bottleneck on knowledge acquisition. What do we mean by that is that getting the information from the medical doctor and from the pathologist and from the pharma people, getting this knowledge and translating this knowledge in a set of rules that had to be implemented within the system, this was very time consuming and it was hard. So it takes forever for you to interview a medical doctor on a particular field, and pay attention to this. It was doing tasks that were exclusively for bacteria infections. So it would not treat, for example, it would not give recommendations about the flu or the cold, anything that were virus related, it would not take care of. So getting the information from that particular field and coding that into the tool, was actually a bottleneck. It would take a lot of time. One extra version, one development of the AIMM software that came a few years later, it was actually comprised of about 5 to 7 years of interviews with medical doctors, just to improve this a little bit. Okay, so the bottleneck on getting this information coded was actually quite hard. The other thing was scalability. So what do we mean by that? Sometimes the problem can have increased complexity. And as complexity increases, the number of rules will increase pretty much exponentially. So here, we were talking about one particular issue was bacterial infections. And we had about 600 rules that had to be manually coded. Now, suppose that we were also looking at, I don't know, let's say viral infections as well. Right? So to add that, instead of having 600 rules, it could be that it would have roughly 3,000 new rules instead. Right? Then the next thing is flexibility. So these systems, they are quite specific. So we are talking again about a system that was dealing with information, with data from bacterial infections. If we were to ask questions outside bacterial infections, it would pretty much fail. It was not designed for that. Right? So lack of flexibility, and then finally inability to learn on its own. That's what I mean. It's not that the system would see new information and register that new information and keep that registered for new cases. It would not learn from new experience at all. We would have to go back into the system and write new rules manually in order for it to learn about those new stuff. Okay? So these were the challenges, and then in the 90s, that's when we started having data-driven approaches. And what do I mean by that in terms of data-driven approach? What happens is that in the 90s, it got much cheaper for us to get computational power. That's exactly when most of the families around the world started getting, for example, personal computers at their homes, right? And as computing power got, higher, so faster processors, more memory, and then the possibility of using multiple processors to compute one single example, one single function, it would allow back then for us to handle more complex computations. Now, the other thing is that, again, starting at the 90s, we started generating way more data than what we could handle manually. So this digital revolution back then made available vast amounts of data, and then to process all that data, we would have to use, again, this higher computing power that we were getting available back then. Just to give you an idea, how many of you, raise your hand, if you do not have a cell phone? Right? Now, if you get your cell phone, we can see things like, what were you doing yesterday at 11 a.m.? Just go to Google Maps and click on timeline. It will show exactly where you were yesterday or last year. If you go to this website by Google called myactivity.google.com and you log in with your email, it opens like a new search type of thing. You can search for voices. So you ask it for voices, and then you will see that your phone records your voices randomly all along the years that you've been using. And sometimes like 3 in the morning, without you clicking on anything, it's recording and it's saved there, by the way. So pay attention to what you guys are doing, right? With your cell phones on. So make sure you turn them off, because it's saving every bit of information. Now, why am I saying this? It's just because it is extremely easy for us to generate data. So some of you, you have your cell phones, for example, are tracking how many steps you're taking every day. And some of you, like this girl over here, right, Samar, she's pretty much like, I didn't walk 10,000 steps today. I have to go to, I don't know, to the restaurant, and I will not take a car. I will just walk to make sure that I'll get my 10,000 steps. Right? And then, on this very same system, that's where you get your appointment with your medical doctor. Right? And then it's just a matter of starting correlating one thing to another. It's just a lot of information that we are generating today. To give you an idea, there is a paranoid thesis. It's not proven, it's just a thesis, okay? That there is, for example, a partnership since 2003, I guess, between Google and Homeland Security in the US. In what sense? That every time that you try to cross the border and you get to the airport and you show your passport, pay attention, by the way, if you're applying to a US visa right now, they ask you, what is your social media ID? What is the email that you have been using for the past 5 years? So the theory goes by like this. When you get to the border and you show your passport, Google shows the immigration official not the contents of your email. They say they do not show that, but they show what are the ads that appear inside your Gmail for the immigration official. So why is that important? I will give you just one particular case. Suppose that the ads that appear to your email, inside your Gmail, is ads about fireworks. And then you get to the border in the US, and the immigration official sees, well, you have been, right before your trip, you got like 10 ads about fireworks on your email. What do you think that the immigration official will think about you? Is it because it's New Year's or it's your birthday? Probably not. They will probably associate that with explosives in general, right? And that will be a nightmare for you to go through the border. One particular case actually happened about 10 years ago of an Australian guy who was going to the US, and he mentioned on Twitter something like this: I have this new gig and I'm going to New York. What happens is that in Australia, when we mention I have this new gig, it's like I have this new plan, I have a new thing coming on, I have a new trip, that's it. And he just posted that. The guy who read that at the border understood that he had a new job in the US, and then refused entry for that particular guy. Okay? So what is it that I'm trying to tell you here? Everything that we are doing today is being recorded somehow, right? You are on your cell phone, for example, you guys were just a few minutes ago clicking on your cell phone. It is recording that you are sit down on these particular GPS coordinates in the world from 11 a.m. to noon, for example. And these will be carried on. So when you guys, for example, when you guys drive by a shopping mall and you get like that SMS coming in on your cell phone, just saying, hey, your preferred store, I don't know, Heringe, for example, or Mac for the girls, whatever store is it that you like the most, we have sales here today, and if you use this coupon code, you're gonna get 10% off. And that SMS just gets to your cell phone as soon as you get close to the shopping mall. That's how things are working today, right? So everything that we are doing is generating a lot of data. And the question is, how do we process all this to make decisions that are well informed, right? So back then, our slide is messed up, and I apologize for that. But in the 90s, we started getting updates to existing algorithms. So we would get updates in the sense of making those algorithms more efficient and making those algorithms aware of big data scenarios. So for example, back in the 90s was actually when one of the most used tools in R in particular was developed in the sense that when you have a regression model and you get new data, you don't need to refit the whole model with the new data combined with the old data. You can just ask for actual updates on the parameters just by showing the new data, and it will process only this new bit of information that you got, right? And then that's when we started shifting from that scenario where we would start with hypothesis and we would start from the data to, for example, come up with new hypotheses. It was like the other way around. So what are the main ideas that we have to consider in terms of machine learning? I want to start with 3 simple definitions, just to make sure that we are on the same page there. In terms of artificial intelligence, it is a field that is very broad. And within that field, we aim to create systems that behave like the human brain. That's it. No more than that. But now, when we are talking about machine learning, we are talking about a specific part of AI that aims to learn patterns from the data. And by the way, just a parenthesis here, you guys will probably hear from now on a lot of discussion between machine learning and statistical learning. I will leave that to you to consider this a little bit, but those are definitions that have been discussed more and more often. And then within machine learning, there is another field. Let's come back here. Within machine learning, there is this other field called deep learning, where we are talking about a specific type of model that is called neural networks with several layers within it. Okay? Now, again, back in the 90s, etc., that's when we started hearing a lot about decision trees, random forest, SVMs, and neural networks. Again, it's not that these guys here were developed in the 90s or were just developed. No, they were already presented to the scientific community like in the 70s, many of them. But Because we had more computer power, that's when we started being able to use these algorithms to process these amount of data. And that's why they started getting a little bit more famous and got to the level that we have it today, right? Oh, seriously? Again, so let's think about types of healthcare data. So when we are talking about healthcare, there are a lot of scenarios that we can think of where data are being generated. One particular type of data that has been actually discussed way too much lately, and you guys will understand why, is the electronic health records. So in Brazilian Portuguese, these are prontuários, but the electronic version of prontuários, okay? And what happens here is that these records, they store two different types of information, of data. One type that we call structured data, and another type that we call unstructured data. Do you guys have an idea of what is structured data versus unstructured data? So the first one, think about an Excel file, like a table, and you get the visits of your patient, visit 1, visit 2, visit 3, etc. And for every visit, you record, for example, the heart frequency of your patient. So on visit 1, heart frequency was, I don't know, 72, then 90, then 63, etc. So this has a well-known structure. But now, suppose that you are a professional that work with voice and speech. So you have a text, and then you ask your patient to read that text. And now, instead of recording a number, what you have is voice. That's the data. How do you save voice in an Excel table? Ideas? How do you do that?
Not possible.
Actually, you don't. That's as simple as that. And that's why it is unstructured, right? So, for example, think about on your cell phones, for example. I bet most of you use WhatsApp. If you are an Apple user, if you have an iPhone, all the voice messages that you send are being recorded on iCloud. And there is a copy of that there on iCloud. If you don't touch your phone and you just install the app, everything is being copied to iCloud every time. That's why your iCloud uses like 100 gigabytes and you do not know why. Right? That's because you have been receiving a lot of videos and sending videos, and everything is being copied over the cloud without your knowledge, probably. Okay? So those informations, they are data without a structure. So suppose you are, I don't know, let's say a pediatrician, and then you ask for a functional MRI of a particular baby or a kid, a toddler. When you get this functional MRI, that's pretty much a video of the brain of that particular patient working on real time. And that information you cannot save within a table. It's a separated thing. So that's data without structure. And then we have all the image data. And when I'm talking about image data, I'm talking pretty much about static image data. So an X-ray, magnetic resonance, or CT scan, for example. And then most of you may be using your cell phones or even smartwatches, and these things are recording vital data on you, like arrhythmias and heart rate, number of steps that you're walking every day, number of steps that you are, well, actually stair steps that you're walking every single day. And then there is something new coming on, which is omics data. So medical doctors are now getting to the point where they are trying to associate, is there any information hidden in your DNA or RNA or within your protein network that is actually able to predict what's going to happen to you in terms of health? Okay? Now, the point that we have here right now is that we are looking at different type of data, and all these data at the same time, they can be used to predict what is it that is happening to a patient and how should I treat that particular patient. So why am I highlighting this? It's because when we are back to the books and we're studying statistical models that we can fit, etc., most of the times we are considering the cases and only the cases where we can save data to a table, right? If you guys go to your preferred software and try to fit a regression model, you will see that it will ask you, what are the variables that you want to use to predict the response that you are giving me? But now, suppose that, do you guys know what is going on in soccer with this footballer called Izquierdo? Okay, so let's take that example, that particular example. So what is the type of data that our regression models would expect about that? It would expect things like, what's the weight, what's his height, what's the heart frequency, and can we make, I don't know, a logistic regression to predict whether he's getting better within 10 days or not. This could be it, but, and this is the type of thing that we have been trained to do. But now, take the case that this guy went to Albert Einstein Hospital and they got, for example, functional MRI on his brain. So they have like this movie, it's pretty much a movie that takes like 30 minutes movie on different slices of his brain, showing exactly what is happening and how the blood is flowing through his brain in every single slice that that machine can detect. So how do I get this information from the movie and put inside my regression model to predict whether he's going to get better within 10 days or not? So that's the type of thing we have been not being trained to do, right? And that's one of the things that we want to incorporate, and I want you guys to think about how is it that we do this particular task. Now, think about this. These new type of data have one particular question, one particular point of interest that is called dimensionality. So there is this particular field in medicine called precision medicine that I started mentioning to you. We want to look at your DNA and have an idea. For example, that's one thing that we already do. Looking at your DNA, I know what is the type of drug that you are supposed to take to control cholesterol, just based on your DNA, right? And then many of you, I bet some of you at least take this particular drug. It's called statin. And then as statins, they depend on the ancestry of the patient. So if your ancestry comes from Europe, then the medication here in Brazil for you is called simvastatina. However, if your ancestry comes from Africa, then the medication for you in Brazil is called rosuvastatina. And that's why you get to people and you're like, okay, your cholesterol is high, I'm taking simvastatina. Why don't you take this? And then the person starts taking it, and the person says, well, I've been using it for a year, and it made no difference whatsoever on my health. It didn't improve my cholesterol levels at all. So that's probably because you're taking the wrong drug. And that type of information is hidden somewhere in your DNA. And we can detect that without a lot of effort. But now the problem that we have here is that if I take your DNA and pretend that it is a rule, and I make this rule as long as it needs to be, it's a rule that has 3 billion positions. And then, if we are a regular statistician and we are like, okay, let's find which one is important to predict cholesterol levels, you're gonna have a regression model that has like 3 billion predictors, and then you have to come up with a way of solving the following question. I know that 3 billion predictors is way too much. I want to find what is the smallest set, I don't know, 10 locations, 100 locations, I don't know. I want to find a smaller set that is important for me to predict cholesterol levels, because I'm unable to use 3 billion things, right? So the problem of dimensionality is something that is gonna hit us very hard and very soon, by the way. Why am I saying this? Let me give you another idea. If we are talking about genes, humans have roughly 20 to 20,000 genes. And then people are like, okay, I want to model a network of genes. I want to know how these genes correlate one to the other, etc. When you think about 20,000 genes, and you think about a correlation matrix, what is 20,000 squared? Right? It's like 400 million correlation coefficients that you would like to compute. Maybe half of that because it's symmetrical. But still, you will need a lot of data to be able to estimate that. And 2, you're going to need a lot of computer power to estimate that. That's why, for example, in statistical modeling within statistical genetics, we sometimes make hypotheses that are unreal, and we know they are, but that's because we lack methods. So to give you an idea, here at the hospital at Unicamp, we get epilepsy patients who are 3 to 5 years old, okay? And then when we are modeling the gene network for those particular subjects, we pretend that all genes are independent between themselves, because computing this correlation matrix is something that is unfeasible. Or, depending on what we have in hand, we start with additional strategies to model that, like Bayesian networks or Bayesian models in general. Okay? But the thing that I want to highlight here is that high dimensionality is something that will hit us very hard, because it's very, very easy for us to generate data today. And what happens is that when we generate data, we are generating data without learning how to analyze these high-dimensional data sets. The second thing that happens quite a lot is that records for patients often have missing data. Why do we have that? How many of you probably had to skip one doctor appointment? You had a doctor appointment scheduled for tomorrow, but then if you are a student, you had an exam, and you're like, okay, I would prefer to take the exam and later I go to the hospital and go to my appointment. Then you have a missing data right there, right? And then how is it that we handle these missing data in order to, for example, train machine learning models? Can we just remove that particular observation? I'm not saying that there is a right yes or no answer for this, okay? But for whatever solution that you propose, there will be a criticism, right? Because if you choose the path that I will remove every observation that has at least one missing data, you're probably going to end up with 0 observations at the end. Because everybody will have a missing observation somewhere, right? So we have to think about that. And the other thing is all these different data sets, they are different in nature. So how do I combine data that are like medical records with images, with, I don't know, let's say you run an ECG and then you have a curve of how your heart is working, and then how do you combine that signal with image and with structured data to run a model to predict something? So data integration here is something that I see as a big opportunity for us to start working on. How do I combine all this in order to be able to train these models? Now, if you guys are thinking, okay, I see how these data are generated, I see how they can be used, etc. But what are the tools that we can use in order to fit these particular models? The 2 main languages, and they are not the only ones, by the way, let me make this clear, but the 2 main programming languages that are being used for machine learning in general is R and Python. R is more in the sense, it's being used more in the sense on how do I fit the models, and while Python is being used as, okay, I have the data and I need this thing ready as a product. And then we have solutions that are already implemented within Python for that. Note that most of the discussion here is not about who is faster. Okay, that's not a problem, really. But we are talking about what is it that we want to do. If you are in the working in the sense that I want to analyze the core details of a particular model, usually Python will not allow you to explore the insides of a model. That's why most of the people will choose to work with R. On the other side, if you are working for a company that has this particular product, it's ready, they have this very nice website, and they want to introduce a machine learning model inside their website. So that's why people usually choose Python, because Python talks well with all these technologies that we have out there. Okay, so it really depends on what is it that you're going to use your models for. But there is also a set of platforms that you can use. You don't have to go to R or Python and write down your models manually and try to fit them. There are whole platforms like Google Cloud ML for machine learning, which is a suite of tools and services that have been developed by Google to expedite the deployment and the management of machine learning models. Okay? They are built in a way that they have at least these five main features. The first one is this Vertex AI, which is a platform that already combines all the main tools for machine learning like TensorFlow, PyTorch, scikit-learn. They integrate all this already inside their systems. So you don't have to worry about how is it that I do in order to make this code to run faster or to run more efficiently or to use all the processors that I have on my computer. We don't have to worry about that. Now, the other thing that Google Cloud offers within the ML platform is this thing called BigQuery. So if you have your data and your data is already in a SQL database or something that looks like a table, you don't have to export your data to CSV or whatever format, a Parquet, whatever is it that your software needs. All you have to do is tell Google, my data is within a SQL database, and all the methods are already available right there. Okay, so you can ask it to run things like create a neural network from the SQL database, and it will do it automatically. Now, the other thing is the hub, the AI hub. So that is actually a very powerful tool because it is a repository for example, notebooks, pipelines, and pre-trained models that other people have already developed. And you don't need to write a single line of code. You can just rerun. That's it. So to give you an idea, if someone there already created a model that looks at cells, at images of cells, and defines and predicts if that cell is infected by whatever, yes or no, it is infected, it is not, this person can save this model that was pre-trained on this repository, and then you can just reuse. You don't have to code anymore. You just reuse. Now, other things that are quite nice within that particular platform is, suppose that you are designing an expert system, just like the one I started talking about. But instead of asking questions that the medical doctor has to type the answers, your system asks the question using voice. And then the doctor replies with his voice. This is the nice thing about Google, because they have all these tools already ready for you. You can just say, take the voice and convert the voice to a table or to a text. And then it will do that automatically for you. You don't have to know the tiny little details. It will just structure the data for you. And then you can use that result into your model, right? And the other thing is that Google took the time to develop new hardware. This is a type of processor that we cannot buy here, or actually we cannot buy at all, because it was developed by Google exclusively to run models from this software, from TensorFlow. So a model that takes, let's say, 3 hours to run on my computer, if I run on a TPU, it will take like 2 or 3 seconds. It's quite fast. Okay? And it's an exclusive hardware that only Google Computing Cloud has access to. Nobody else has. There is more than one, but there are competitors to that. There is Azure from Microsoft, there is AWS SageMaker from Amazon. So what Amazon has been doing is focusing on efficiency and security. Why? Because Amazon identified that the niche of clients that they want are companies in general. So how is it that they are doing this? So they have like all these tools that make simpler for you to do cleaning of your data and transformation on your data, and you don't have to write any code to do that. You can just point, this is my table, I want to visualize the data, and it has special types of visualizations that allows you to identify, well, this number here was probably an error, and then you can go back and fix it, and go back and forth without writing any type of code. And then it has all those pre-built ML models that you can use. Again, nothing about writing code to fit these particular models. You can pretty much just drag and drop the models that you want and say run, and it will run. And what are the type of models that we can run there? You can do regression, you can do clustering, image processing, but there is something quite cool that is starting to happen. Well, it's been happening for the past 2 to 3 years, and I think it will take a little bit more time for us to have a final product that is something called autopilot. So within that context of autopilot, you can just show your data and you specify your data saying, this is the response, these are my predictors, etc., etc. And the software starts analyzing your data and selects what are the most appropriate machine learning models that can be fit there. But it does not tell that to you necessarily. It also starts fitting the model and identifying, detecting what are the hyperparameters that you need for those models to work on your particular data. So this is the machine learning version of what GitHub has been doing with their Copilot in terms of writing code. Now, one thing that Amazon offers to the clients that most of the competitors do not is the tools for you to make real-time inference. So there is something quite neat about real-time inference. So suppose that you are, for example, working on a company and you are receiving payments through credit card online. So real-time inference will allow you to observe the payments coming through in real time and decide, again, in real time, whether those payments are legit or if they are frauds. Okay? So that's one of the applications that Amazon has been using. But we need to be aware that these type of tools could also be used for healthcare. So what is the major attention point that we are getting right now in terms of health in the world? It's like Mpox infections, right? So one thing that we could do using these particular tools is actually tracking these cases as each country and their health ministry start releasing data. And we can do like real-time surveillance of infections. Just to give you an idea, this type of tool is already used in Brazil, for example, for the producers of oranges. And how is it that these guys are using it? Well, there is a particular disease, a Lyme disease, that can actually kill the whole set of orange trees that they have on their plantation. And what they are doing is actually keeping records of people reporting infections within the state of São Paulo. And then once it gets to a particular level, what they do, they raise a red flag and they go on site to create a physical barrier for the Lyme disease to not spread to other plantations, to other farms, right? So these are the type of applications that we have. And then Amazon has been focusing a lot on security and compliance. So in terms of compliance, for example, the type of thing that they are looking at, they want to make sure, for example, that the records were not modified after they were stored. For example, that's one idea. That's how you detect, by the way, I'm not talking about politics here, but that's how you detect when people change their records on their vaccination cards. That's the type of thing that they do. So what is it that we want to pay attention in terms of the machine learning process? There are quite a few steps here that are used. So we started with getting the data from different sources. We clean our data, we build the model, we try to understand the model, and then we do visualization. You guys will work a little bit, for example, on the model building tomorrow, I guess, and on cleaning data as well. But I want you to understand the high-level concepts that we are dealing with here. So on data cleaning, we need to work towards removing noise that we have on our data. And sometimes, I'm not saying always, sometimes it may be of interest of working and sometimes removing outliers from the data set. Pay attention to the word sometimes, please. I'm not defending the thesis that if you see an outlier, you should remove it. That's not what I'm saying. Now, the other thing is we have to remember that the data that we have different variables, and these variables are in different scales. Example here, one variable is age, which is stored in years. Another variable is weight, that is stored in kilograms. When I fit a machine learning model, it could be that the size of these variables will drive the whole model fitting. Why? Because they are in different scales, just because of that. A very extreme example, suppose that you work on these companies, on freight companies, that gets like a lot of things on boats, and they transport your things from Europe to Brazil, for example, on a boat. Or get those containers from China and bring to the Americas in general. One variable could be the number of containers on one boat, and the other variable could be the total weight of load on that particular boat. The number of containers is something like 100 containers, but then the weight could be something like 300,000 kilograms. And then, because the number 300,000 is so big, it could drive the whole model fitting step. So one important step that we have here is normalization, that is meant to bring all these variables to the same scale, because once they are on the same scale, that's when we start fitting the model. Okay? One other thing, by the way, about normalization, well, I will save this a little bit and say a little bit later. The next step is something regarding missing data. We should consider, is it that we are gonna do data imputation Is it that I'm going to remove missing data? That's one thing that should be discussed within the group. And if I'm going to impute data, am I going to use SMOT, mean, or the k nearest neighbors to do imputation? And the last step is something called feature engineering. I want to highlight this particular thing here, because it's the task where we create new variables or new features, if you're coming from a computer science background, that will be used to improve the model accuracy. And the parenthesis bit here is something that for me is quite important, or to protect privacy. So here's an idea. Let's think about finance in general, okay? In terms of finance, every country has a company or an institution that creates credit scores. In Brazil, it's somebody called Serasa, right? So what is it that you think that Serasa has in their databases? They have, I don't know, the tax number, our CPFs, they have the tax number, but they have a lot of knowledge about every single person that they are tracking. What are the type of information that they have? They have address, they have salary, they have average costs of their credit card, the average limit of their credit card. All these information are actually very private information for every single person, right? And what happens is that if you own a store, you sell cars, and you want to check the credit score of your client before selling the car, it's not that Serasa will show the salary of this person is this, or the address is this other one, or the average credit card bill is this thing. Serasa will not show that, because those are private information, private data. What they will show is some sort of score, which in our case here in Brazil, it goes from 0 to 1,000, right? And this score combines all these other private information. So instead of saying, of telling the owner of the store that the salary of this person is 10,000 reais, and this person has 5 TVs at their house and owns 2 houses, etc., etc., what they do, they say, this person has a score of 700. That's it. So it's safer to share the score than sharing the private information of each person. The same thing applies to healthcare. I cannot share or disclose particular information, private information of the patients. And then when we are fitting our models, we have to be careful about this. So instead of sharing or using the raw information, what we do often is to transform this data into something else. It could be, very simple example, let's create a PCA score or a UMAP score and use these scores instead of using the actual individual data. Why? Because sometimes there are data leaks in different places, and we want to avoid the information that is private to that particular patient to be leaked and somehow be used in a bad way towards that particular patient. Okay? Oh, look at this. Come on. So for model building and evaluation, things that you guys will need to pay attention to. What is the size of data that you have? Is it simple to interpret the findings that we got from our particular model? And what are the computational resources that we have? So I left here a few questions that you guys need to ask yourselves often. So let's say you are looking at the, I don't know, the number of cases of malaria or dengue or mpox that are happening in a particular location. Let's say that you're looking at that. And you have a few options here. You can fit a very complex neural network like a deep learning model, or you can fit, for example, a logistic regression. The question that I want you guys to always ask is the most complex model always the best option? The best option? Sometimes it's not. Especially if the team that you are working with is a team with people from different disciplines. You are the statistician or the data analyst, but then you have the mathematician and you have the medical doctor and the nurse. How do you explain a deep learning model to a medical doctor? And here's the important bit. The medical doctor will ask the following. Okay, I understand that we are getting more cases, for example, in São Paulo State. Why? And then when you get to your deep learning model, it's not easily explainable. It might be that with a simpler model, you might be able to explain this a little bit better. And I think that the important question here for us to keep in mind is what Tuki brought us a while back. All the models are wrong, but some are useful. So is this model useful? That's the type of thing that we want to focus on. And in the particular case of healthcare, we need those clinicians to be able to understand what is it that we are trying to communicate. So there are a few metrics that you guys will see into more details tomorrow. But we could use things like mean square error as a metric to assess whether a model is working well or not. There is sensitivity, specificity. There is here, I'm sure that you guys can read, it's written ROC curve that is showing actually the discrimination power of your model of detecting whether you're looking at a case or at a control. But we need to use these metrics in order to be able to assess whether or not our model is working fine or not. There is one trick, by the way. Let me remind you of this, and again, you guys will see a little bit more details on this tomorrow. There is a strong bias for us to look at models that are overfitting. So what do I mean by that? I have my particular data set, and most of the people are trained to fit the best model for this particular data set. Now, if my data set is comprised of patients, it's just like I'm training my model to do the best it can do on this set of 100 patients that I have here. However, when a new patient walks in the clinic on the next day, the model fails beautifully. So this is overfitting. It works very well for the set where I trained, but when I get new patients, it just fails, right? So one strategy that we have been using a lot to protect us against overfitting is called cross-validation. So if we look at our data set, and our whole data set is just one row of these points. Okay, exact this row. So one idea of cross-validation is separating one portion of this data, and we hide these test data, we hide this test data in a drawer somewhere. We do not touch this first part of the data. Now, I come back to the training set, the remaining observations, and I fit my model here. But I told you guys, well, there are a lot of metrics that we can use. We can use sensitivity, accuracy, mean square error if you're looking at regression models, the ones on the slide before. So we have all these metrics here. So what do? We fit the model here, but when it's time to compute the metrics, I compute the metrics on the test data. So what is it that we are doing here? Let's try to understand this with an analogy. These guys here, all of them, are the 100 patients that I have in my clinic. What did I do? I got 20 out of them, and I used 80 of them to fit the model. But now it's time for me to say if the model is good or bad. How do I do that? I have to compute metrics, quality metrics, like sensitivity, like specificity or accuracy. It will only work if my model performs well on the 20 patients that the model did not see. Right? So what I do, I come back to these 20 that were hidden in my drawer, and I measure, for example, the accuracy here. And now what I do, I shift. Instead of leaving, for example, these 20 out, I will leave these other 20 out. And then redo the model and redo the quality assessment until I run through the whole data set. Now, once I do this for the whole data set, I can have, for example, an average accuracy for the observations that were out of the data set. So these observations that were out, they work as they were the new patients that were about to come to the clinic. And then I could do the assessment on these guys here instead of looking at the actual training data. So this is what you guys will do tomorrow, a little bit, I think, with Samara and Tatiana. Now, in terms of applications, we are going towards the end here. Applications that we have been working quite often in these past few years is doing diagnosis of diseases and predictive analysis. So we want to look at features, at characteristics of the patient, and to be able to predict what is it that is happening with that particular patient. Now, more than that, now that I know, or I have at least a hypothesis of what's happening to that particular patient, I want to be able to have better advice in terms of treatments that we should deliver for that particular patient. So to give you an idea of how this is working, here at Unicamp, as I mentioned, we are looking at these pediatric patients of epilepsy. To tell you a little bit of this story, these patients get to our clinic when they are about 3 years old. And do you guys have an idea of how many years we need to come up with a treatment for a kid that arrived at 3 years old? How many of you think that we need about 1 year? Or 2? Or 3? 4? It takes about 12 to 15 years for us to figure it out what is the best combination of drugs that will treat, not cure, that will treat that particular patient, okay? Now, think about this. We get 100 patients and they are 3-year-olds. And then we work for 15 years in a row. And then they are turning 18 years old. And for 60 of them, we can tell the parents, go to the pharmacy and buy this combination of drugs that will reduce the symptoms on your kid. For the other 40, we have to say there are no drugs on the pharmacies that will treat your kid. And the recommendation is come here later on and we will open his brain and cut out, literally, a piece of the brain of your son or of your daughter. And this will reduce the number of epilepsy seizures that they are having. So we had to wait like 15 years in average. Please keep in mind that I'm talking in average. There are some that will be within a year. There are some that will be within 25 years. But in average, 15 years. And just come back because we're going to open their head, get the brain cut out, a piece of their brain, and things will get better. They usually do. But the thing is, that family had to wait 15 years in average to receive that note, right? What we were able to do, we are looking at particular mutations on their DNA, and we identified 72 places in the DNA that can actually predict if that kid will respond to the drugs that we have on the pharmacy, okay? But to make like a little game here, what we also did was we got the records of all these patients and we showed them to the best neurologists that we had access to. And we asked them, can you look at the medical records of these kids and tell me who are the kids that need surgery and who are the kids that we are going to be able to treat with drugs? What do you think was the rate of accuracy of the medical doctors? They got right about 42% of them, right? And let me highlight this. For you to have a bachelor in medicine, to become a medical doctor, it's like 6 years, plus 2 years of master's, plus 4 to 5 years of doctorate, and 2 to 3 years of rotation, plus a few postdoctoral studies, etc., and plus that, like 20 years in clinic. And these guys get right, just looking at the medical records, about 42% of them. And that was like, for me in particular, I could say, hey, my first year undergrad students in statistics can perform better than you with all this training. So all I have to do is to get my students with a white jaleco, that I do not know how to say in English, to an office, and I give them a coin. Every time that a new patient gets in, he tosses the coin, and if it's head, it's surgery. If it's not, it's drugs. And we keep doing this. In the long run, the student will get right 50% of the cases, while the medical doctor got 42, with all his expertise, right? But we identified these 72 pieces of DNA, and when certain modifications, mutations on these 72 locations happen, we can actually predict about 84% right of who needs the surgery and who needs the drugs. So it's not 100%, but it's way better than 42. And we are working towards increasing these a little bit more. And that's how the clinic is going today. So we are looking at these things of personalized medicine. But then there are applications, again, on outbreak predictions and also drug resistance modeling in general. So just think about what was the preferred antibiotics during the pandemics. Was it azithromycin?
Yes.
Right? So, for example, in northeast Brazil right now is happening an outbreak of, I forgot the name, sarna. Do you know what sarna is? Right? So there is an outbreak of sarna in northeast Brazil. And why is there that particular outbreak? The reason for that is that the main treatment for that is exactly azithromycin. And sorry, not azithromycin, it's ivermectina. And then people started misusing ivermectina, and now they are drug resistant to that particular thing. And by the way, these are cases that actually can get really bad very, very, very fast, right? So I think this is towards our end. Things that I want to highlight here, when we are talking about machine learning and artificial intelligence within healthcare, I think, honestly, I believe in this idea that we have to work within a team of people with different specialities. So we have the person who knows how to do data analysis, for example, that's important, but we need the clinicians, we need people who are working towards ethics, and how is it that we put all of this together in order to provide a better healthcare, protecting the patient with the best statistical efficiency that we can get at that particular model, at that particular point. One other thing that we need to highlight is that it's not all data sets that must be used. If we have trash in, we have trash out. So we have to make curation of our data sets and make sure that we are using high quality and well annotated data sets. And in particular, we have to be careful with validation. Our models are expected to work in general cases and not in particular cases. Okay? So when I'm mentioning here use diverse data sets, I will give you two very simple examples outside healthcare for you to understand. So the first iteration that Dell, the computing making company, that Dell had with their face identification to unlock computers, it failed every single time that you had a person that had ancestry from Africa. So if you were white and Caucasian, the software worked just fine. But then if you're like me, the computer would not unlock at all. At all. You had to send the computer back for assistance for them to turn off that in order for you to be able to operate the computer. The other example was for the iPhone. The iPhone, if you, on the first rounds of Face ID, if you had any person from China, it would unlock the phone. So it's pretty much that very, very bad joke that we have that all Chinese look the same, right? So what was happening there? When they were training the models to do the unlocking, they probably had one or two people that were coming from Asia. So it was not getting the diversity that was required to identify uniquely one particular person. So we have to be careful with this. This is actually what happens, for example, with most of the drug development systems that we have today. Why am I mentioning this? Because when we are talking about a new drug, this drug is being tested most of the time on Caucasians that are coming either from Europe or North United States using diverse data sets. That's one thing that we want to highlight. And just pay attention to this continuous monitoring of these models. So once we train a particular model, it's not that that model will work forever with the same efficiency as it started. We need to update that regularly. Now, challenges that we will have towards this is confidentiality. We need to take care about this bias on the data sets that we are using. We need this model to be general and work in general cases. And we want to be able to interpret what the model wants to tell us. These are things that we have to keep in mind. And if you guys are looking on questions like, what is it that I want to research right now? These are probably good pointers for you to start with. How do we make those things to happen, right? So what is it that we are getting in the near future? And I apologize for the dimensions not fitting here. So one thing is explainable AI. That's one thing that people are working a lot recently. What is it? I have a very complex neural network model, for example, and I want to know why it took that particular decision. That's it. Think about Tesla cars. I want to know why it decided to take that turn even though the light was red. That's what we want to do. Now, the other thing, this is one thing that I like a lot, is called federated learning. We are talking about machine learning, and what we think is that I have this supercomputer, and this supercomputer has all the data that I need, and I fit the model magically. This is how it works in general for classical machine learning. On federated learning, think about your cell phones. The cell phone of each of you guys has information about you. How is it that Google and Apple combine the knowledge that they have on each of your cell phones in order to do recommendations for you, in order to say, hey, you have to walk 2.4 kilometers more in order to achieve a given health standard? Now, this is important because when you get to hospitals, hospitals cannot share the data on their patients. If I want a model that will look at an X-ray and decide if it's cancer or not, I cannot share the data across the hospitals because those are private data. So federated learning will take care of this. And then this thing that I already mentioned about automatic machine learning, and now here the opportunity that I see is surveillance on these particular outbreaks that we need to take care using these real-time inference tools that are being developed right now. So thank you. If you guys have questions, threats, or
That was a great one. Thank you so much.
this is out of that.
That was great, isn't it? Yeah. So we have just limited time for questions. This is a very exhaustive lecture, and we want to thank you for coming to enlighten us. Let's give him another round of applause. Question? So let me just open the floor. You didn't mention generative AI.
I did not, indeed.
Okay, so can you say something?
So let's talk a bit about generative AI. So what we have in this particular case, what we have seen on this particular case, we are looking at particular models that are looking at things like text, and they analyze the flow of text. What are the words that are coming? Every time that I use this word, do we have necessarily this other word happening in general, okay? So these are the scenarios that we are looking at. And we have this model that will use the input that you give in terms of text. So you could describe things like, Can you tell me anything about Tukey and the models that must be useful? The model will analyze this particular question and try to identify patterns on these and go back to their knowledge base and try to see if it has information that match that type of query. The problem here is that it's not curated, right? So it can be delusional sometimes. And it will probably, if you ask ChatGPT, for example, can you give me ideas of beach in Campinas? It will find an address in Sousas, maybe, just saying at this particular location you have a beach. Why? Well, because that's where people like to go during the weekends, and that's what people do with beach. They go on the weekends and they have fun, etc. Now, what we are having on top of that is that the response of these particular models, they are being associated with new features. So instead of having, for example, a textual response, I could start asking questions like, generate for me an image of a dolphin at Lagoa do Taquaral. And it will try to identify what is Lagoa do Taquaral and try to identify what are the images that are associated to that, and again, generate on top of this information by matching the request to what is recorded on the knowledge base. One particular development that I think that is quite important for you to keep in mind is that all these tools like GPT or Gemini and Claude, they will clearly say, pay attention that not all the results that we are giving here are factual. They can be just an illusion of the model because the model found this pattern on my knowledge base and it tries to interpolate. But there is one particular tool that I would like to bring to your attention that is actually developed by Google. Let me show you this real quick. So if you go to Google and just type notebook AIMM, oh, seriously? Here. So if you type notebook AIMM, so it will give you like this tool here. I don't think it will let me try because it will ask me to log in. But let's, hold on, let me see if here. So what you can do on Notebook AIMM, it is also using this technique of generative AI, but what you do, it has two steps. The first step is that you get the documents that are true. So if you get, for example, a set of articles or a book that you wrote in the past, references that you believe that are true, what you can do is you upload these documents to the Notebook AIMM, just like it's showing here. So you upload those files, and these files can be in any format. It could be like Word documents, it could be PowerPoint or PDF or Markdown. You upload the documents, and then you can say things like, using the documents I have uploaded, please make a summary of what John Tukey said in terms of useful models. And then it will do the same exercise of matching my request to the PCA-like representation of the knowledge base that it just generated from the data that you have uploaded. And it will say, following what is on what is described on reference number 1, John Tukey said that all models are wrong, but only a few are useful. and it will pinpoint what are the references that it used to make that particular claim. So what we are seeing right now is that we are changing the pace a little bit, and instead of having this huge knowledge base that we see from ChatGPT or sometimes from Gemini and Claude, that tries to understand everything about everything, what we are going to start doing is actually creating our smaller set of knowledge and then asking questions about things that are defined on that particular knowledge base. So once you upload, you can ask questions. So it has like this box here where you can ask your question, and those are the references. It starts writing about it, and it pinpoints where it is taking that information from. So I guess that we are moving towards that direction, that within our field, we are going to be able to define what are the gold standard references for what we need, and then we start using Gen AI.
A very short answer. But,
Sorry.
one or two questions?
Okay. Muito obrigado. Thanks so much for your presentation. It is truly insightful. So I've got a question, and the question is, when developing a model, you talked about the need for cross-validation, and I jotted down my question. That you said that there is a need for us to do a sort of cross-validation so that it can accommodate, future data that can be, used for. So I just want to ask that what determines the population or number of tests, the test data? Because in your presentation there was the diagram. Perfect. So I just want to ask that what determines the population of the test data that can be, that can be put aside or hidden while we are looking at the training data. So if I'm having like a large data in total, what's going to determine the number of my test data and the, what I should use for my training data? Thank you.
We are going to stick to undo that one tomorrow in details, but maybe just a short.
So they're gonna give you a few highlights on how to choose that, but usually the way that this splitting here happens is between this side here. It's usually between 60 to 80% of your data, and then the remaining here on testing. And depending on the type of approach that you are using, there is the possibility of splitting these in 3 different sets, which is a little bit more complicated, but it would be something like 70, 15, and 15. But usually 60 to 80% and roughly 20% here. And the way that these observations are selected, it's usually through random sampling, really.
The test data can be interspaced. Can it be interspaced? Or it has to be towards the flanking?
No. This was just to show here, but it can be interspaced in any way that you want, really. It's really random. The only way, or the only scenario where it would have to be something physically like this is if we were looking at time series data. If it was time series data, then it would have to be something like this. But in general, no. Whatever type of splitting would work.
Thank you so much.
So we'll do more of that practically tomorrow, okay? And 1 or 2 more, maybe in Portuguese or English. Anyone? Okay. So please wrap up.
Is my turn? No? Benilton, thank you very much for your presentation. My question is about the interpretability of the models in machine learning, because I think that in general our principles in statistics is to produce model with some kind of parsimony.
Yeah.
So, what is the relationship between the parsimony that we look for in a model, in statistical model, and the goal of produce good predictions that appear to be here in machine learning? There is some possible connection or in a future or solution about that?
Yeah.
Only your opinion. Thank you.
In this case, it's a quick opinion. That's actually what is differing statistical learning from machine learning, right? It's the actual ability for you to make interpretations out of your models from considering a model that has a finite, let me say this way, number of parameters that you can actually bring to interpretation. So that's one particular way that I see this. It's actually the difference that I see when I'm looking at these type of lectures coming from people like Triani versus when I'm looking at the same lecture coming from computer science. What is important to highlight as well is that there was a problem in the past that happened with people from computer science that are bringing them towards the same path of explainable AI and trying to get models that are easier to interpret. There was this scenario in the past where they were looking at X-ray images to diagnose what was the disease, the pulmonary disease that the patient had. And they got a neural network that was getting it right 100% of the time. And they were so excited about it. Look, we got the perfect machine, it gets it right at every single time, etc., etc., etc. And then what they figured eventually was, remember that when you get an X-ray at the corner, sometimes at the corner, you have the initials of the patient. So what the neural network was looking at, it was looking at the initials, and it would cross-relate those initials with the medical records. And then once it found the medical records, it would go to what is the disease that this person has, and it was just reading the medical records, and not that it was analyzing the image of the X-ray itself. So what we are getting at this point is that even when I mentioned the possibility of having these two different views, one coming from statistics and the other one from computer science, we are getting to a way that both tracks are merging towards these models that can be interpreted in a simpler way, instead of looking at that particular model as a black box that nobody can look inside and see what's going on. So we are towards this, and I think that at least today, this difference of a model that has parsimony versus a model that is very complex, it is still under the hood of what is statistical learning versus machine learning.